In this video, we'll be going over lots of examples for simplifying radical expressions involving square roots. We'll be applying the basic techniques for simplifying square roots, such as removing perfect square factors in square roots, rationalizing the denominator, and combining like terms of square roots. So if you need an introduction or a refresher to these concepts, you can watch my previous video, links in the description. So let's look at our first example. How do we simplify square root of 50 plus square root of 98? At first, it might seem like we can't combine like terms to simplify this expression because square root of 50 and square root of 98 are not square roots of the same number. However, you may notice that both square root of 50 and square root of 98 are not in simplest form because the numbers inside the square roots have a perfect square factor. Whenever that's the case, it means that the square roots can be simplified further. So the first thing we should do is simplify square root of 50 and square root of 98 individually. And to do that, the first thing we need to do is to find the prime factorizations for each number. So we'll simplify square root of 50 first. 50 divided by 2 is equal to 25, and 25 divided by 5 is equal to 5. And 5 is a prime number, so we can't factor this any further. So the prime factorization of 50 is 2 times 5 times 5. Whenever we have a pair of repeated prime factors in the prime factorization, it results in a single factor of that number in the answer. So the pair of 5s in the prime factorization of 50 results in a single factor of 5 in the answer without the square root. And this is because square root of 5 times square root of 5 is equal to 5. Whenever we have a single prime factor in the prime factorization, it just results in the square root of that number in our answer. So the single prime factor of 2 here simply results in a multiplication by the square root of 2. So square root of 50 can be simplified as 5 square root of 2. So let's apply the same principles to simplify the square root of 98. So as always, we should find the prime factorization of 98 first. 98 divided by 2 is equal to 49, and 49 divided by 7 is equal to 7. And 7 is a prime number, so we can't factor this any further. And that means the prime factorization of 98 is 2 times 7 times 7. Since we're trying to simplify square root of 98 here, which is the second part of the sum, square root of 50 plus square root of 98, we need to put a plus sign after the 5 square root of 2, which is the simplified form of square root of 50. So we can see a pair of repeated prime factors of 7 here, which will result in a single factor of 7 in our simplified square root. And there's also a single factor of 2 in the prime factorization, and that will just result in a multiplication of the square root of 2. So square root of 98 can be simplified as 7 square root of 2. So to recap, you just need to remember that whenever we have a single pair of repeated prime factors, it results in a single factor of that integer number. And when we have a single prime factor, it results in the square root of that number. So if we look at the expression 5 square root of 2 plus 7 square root of 2, we can simplify this by combining like terms because both 5 square root of 2 and 7 square root of 2 have the square root of 2 term in common. 5 plus 7 is equal to 12. So 5 square root of 2 plus 7 square root of 2 is just equal to 12 square root of 2. And this is our final answer. Alright, so let's do another similar example. It seems like we can't combine like terms in the expression square root of 72 plus square root of 162 because the two square root terms are not the same, but we can try to simplify both terms individually first. So let's simplify square root of 72 first, and to do that, we need to first find the prime factorization of 72. So 72 divided by 2 is 36, and 36 divided by 2 is 18. 18 divided by 2 is 9, and 9 divided by 3 is 3. And 3 is a prime number, so we can't factor this any further. So the prime factorization of 72 is 2 times 2 times 2 times 3 times 3. So we can see a single pair of 2's in the prime factorization, and this results in a single factor of 2 in our answer. And there's also a single pair of 3's, and that'll simply result in a multiplication by 3 in our answer. And then there's also a single factor of 2, and that will just result in a multiplication by the square root of 2. So this expression, 2 times 3 times the square root of 2, is the simplified expression for the square root of 72. So let's move on to simplifying the square root of 162. And to do that, we need to find the prime factorization for 162. So 162 divided by 2 is 81, and 81 divided by 3 is 27. 27 divided by 3 is 9, and 9 divided by 3 is 3. And 3 is a prime number, so we can't factor this any further. So the prime factorization for 162 is 2 times 3 times 3 times 3 times 3. So the next thing to do is to look for pairs of repeated prime factors in the prime factorization. We can see a pair of 3's in the prime factorization, and that will result in a single factor of 3. So we need to write a plus 3 in the answer since we're adding the square root of 162. And then there's a second pair of repeated 3's, so that will result in another multiplication by a factor of 3. So there's also a single factor of 2 in the prime factorization, so we need to multiply by the square root of 2. And this means that the square root of 162 can be simplified as 3 times 3 times the square root of 2. So the next thing to do is to simplify this expression further. 2 times 3 times the square root of 2 in the first part of the sum is simply equal to 6 square root of 2, and 3 times 3 times the square root of 2 is equal to 9 square root of 2. So now both terms, 6 square root of 2 and 9 square root of 2 in this sum, have the square root of 2 term, so we can combine like terms, and since 6 plus 9 is equal to 15, 6 square root of 2 plus 9 square root of 2 is simply equal to 15 square root of 2, and now this expression is simplified, and this is our final answer. Alright, so let's look at a slightly different example. What happens when we have a square root of an entire fraction? Well, the first thing to do is to determine if the fraction is in simplest form, and to do that, we need to find the prime factorizations of both the numerator and denominator. So we'll start with the numerator, which is 24. So 24 divided by 2 is equal to 12. 12 divided by 2 is equal to 6, and 6 divided by 2 is equal to 3. And 3 is a prime number, so we're done, and that means 24 is equal to 2 times 2 times 2 times 3. And we'll do the same with the denominator, 36. So 36 divided by 2 is 18, 18 divided by 2 is 9, and 9 divided by 3 is equal to 3. And 3 is a prime number, so we're done, and this means that 36 is equal to 2 times 2 times 3 times 3. So now what we can do is rewrite the fraction inside the square root, and we can rewrite 24 as 2 times 2 times 2 times 3, because that's the prime factorization of 24 we just found, and the denominator of 36 becomes 2 times 2 times 3 times 3, because that's the prime factorization of 36 we found. So now we can see some common factors in the numerator and denominator that we can cancel out. So there's a 2 in the numerator, and another 2 in the denominator that we can cancel out, and then there's another pair of 2's that we can cancel out, and then there's a pair of 3's in the numerator and denominator that we can cancel out. So this means we're only left with 2 in the numerator and 3 in the denominator, so the entire fraction is just 2 over 3, so this expression is equal to the square root of 2 over 3. So recall that if we have a square root of a fraction, we can rewrite it as a fraction of the individual square roots. So we can rewrite square root of 2 over 3 as square root of 2 divided by the square root of 3, because square root of a divided by b is equal to square root of a divided by the square root of b. The last thing we need to do is to rationalize the denominator, and what this means is we need to ensure that there are no square roots in the denominator. So right now we have a square root of 3 in the denominator, and to get rid of that, we can multiply both the top and bottom parts of the fraction by the square root of 3. So what we'll do is we'll multiply this entire expression throughout by the square root of 3 divided by the square root of 3, and this doesn't change the value of the expression because we are effectively multiplying by 1. To simplify this, we need to multiply square root of 2 and the square root of 3 in the numerator, which turns out to be square root of 6, and in the denominator, square root of 3 times the square root of 3 is equal to 3. So we have rationalized the denominator because the denominator no longer has any square root expressions, and this expression is simplified. So here's an example involving the product of two square roots with fractions. The first thing we can do is check to see if each fraction is in simplest form. So in the first fraction, we can rewrite 15 as 3 times 5, and 30 as 2 times 3 times 5. So in the second fraction, 8 over 7, we can rewrite 8 as 2 times 2 times 2, and the denominator 7 stays the same since it's a prime number and can't be factored any further. So in the first fraction, the 3's cancel out, and so do the 5's. So we're just left with 1 over 2 in the fraction. So we can rewrite the first part of the product as the square root of 1 over 2, but there's nothing that will cancel out in the second fraction, so we rewrite it as the same thing, which is the square root of 2 times 2 times 2 divided by 7. So now we can combine these two fractions as a single fraction, because if we have the product of two square roots, we can always rewrite it as the product of the two values inside a single square root. So this just becomes the square root of 1/2 times the second fraction, which is 2 times 2 times 2 over 7. So the 2 in the denominator in the first fraction cancels out with one of the 2's in the second fraction. So this entire fraction just simplifies to 1 times 2 times 2 in the numerator, which equals 4, and 7 in the denominator. So now we have the square root of 4 over 7, which we can rewrite as the square root of 4 over the square root of 7, and the square root of 4 is just equal to 2, so we can further simplify this as 2 over the square root of 7. So the last thing to do is to rationalize the denominator and get rid of the square root in the bottom part of the fraction. To do this, we need to multiply the fraction throughout by square root of 7 over the square root of 7. What this does is get rid of the square root in the denominator, because 2 times the square root of 7 in the numerator becomes 2 square root of 7, and square root of 7 times square root of 7 is equal to 7. So this expression is now 2 square root of 7 over 7, and you can see that the denominator doesn't have the square root anymore, so we have rationalized the denominator, and this expression is simplified. So here's an example involving a product. To simplify 3 square root 12 times 6 square root 18, we need to multiply both the integer parts and the square root parts. So 3 times 6 is equal to 18, and square root 12 times square root of 18 is equal to square root of 216. So this expression is just equal to 18 square root 216. So we're not done yet, because we can still simplify the square root of 216, and to do that, we need to find the prime factorization of 216. So 216 divided by 2 is 108, and 108 divided by 2 is 54. 54 divided by 2 is 27, and 27 divided by 3 is 9, and then 9 divided by 3 is equal to 3, and 3 is a prime number, so we're done. And this means that 216 can be factored as 2 times 2 times 2 times 3 times 3 times 3. To simplify this expression further, we first rewrite the 18, which stays the same. Then we look at the prime factorization for repeated prime factors. There's a pair of 2's, and this results in a single factor of 2. And then there's also a pair of 3's, which will result in a single factor of 3. There's a single factor of 2 remaining in the prime factorization, which results in the multiplication by the square root of 2, and the remaining 3 translates into a single multiplication by the square root of 3. So now we need to multiply all these terms together. 18 times 2 times 3 is equal to 108, and square root of 2 times the square root of 3 is equal to the square root of 6. So this entire expression is just 108 square root of 6, and this is our final answer. So what do we do when we have a product involving brackets? Well, what we need to do is use the distributive property. Recall that the distributive property states that a times parentheses b plus c is equal to ab plus ac, where we get rid of the brackets and do 2 multiplications instead. So to apply the distributive property to this expression, 4 square root 2 times parentheses 3 square root 2 plus 6 square root 3, we need to multiply 4 square root 2 by 3 square root 2 as our first multiplication, which is the AB term. And then our second multiplication would be 4 square root 2 times 6 square root 3, and that's our AC term as our second multiplication. So now this expression is just equal to 4 square root 2 times 3 square root 2 plus 4 square root 2 times 6 square root 3, because we need to add up the two multiplications according to the distributive property. To simplify this, we need to do the multiplications. So in the first term, 4 times 3 is simply equal to 12, and square root of 2 times square root of 2 is simply equal to 2. Now in the second term, 4 times 6 is equal to 24, so we need to write a plus 24, and then the square root of 2 times the square root of 3 is equal to the square root of 6. So now we can simplify this further, because 12 times 2 in the first term is equal to 24, and the plus 24 square root 6 stays the same. So this means our final answer is just 24 plus 24 square root 6. So here's an example involving the product of two expressions, both with brackets. For this type of problem, we can use the formula listed at the side here. Parentheses a plus b times parentheses c plus d is equal to ab plus ac plus bc plus cd. Basically, what we're doing is multiplying each term in the first brackets by each term in the second brackets exactly once, then adding up all the results. So we would be doing 2 times 2 multiplications, since there are 2 terms in both brackets, which results in 4 multiplications in total. So to use this process on our expression parentheses 2 square root 7 plus 3 square root 5 times parentheses 4 square root 3 plus 6 square root 2, we need to do our first multiplication, which is 2 square root 7 from the first parentheses multiplied by 4 square root 3, which is the first term from the second parentheses. So 2 square root 7 times 4 square root 3, and then we need to multiply 2 square root 7 from the first parentheses by 6 square root 2 from the second parentheses. So now we move on to multiplying 3 square root 5 from the first parentheses with 4 square root 3 in our second parentheses. And then now we do the same with 3 square root 5 multiplied by 6 square root 2, so 3 square root 5 times 6 square root 2. So since we're applying the distributive property repeatedly here, we need to add up each multiplied term as usual, which we already did. So now it's just a matter of simplifying each individual term by doing the multiplications. So in the first term, 2 times 4 is equal to 8, and square root of 7 times the square root of 3 is equal to the square root of 21. So in the second term, 2 times 6 is equal to 12, and square root of 7 times square root of 2 is equal to the square root of 14. So in the third term, 3 times 4 is equal to 12, and square root of 5 times square root of 3 is equal to the square root of 15. And then our last term here, 3 times 6 is equal to 18, and square root of 5 times the square root of 2 is equal to the square root of 10. So if we look at this expression, 8 square root of 21 plus 12 square root 14 plus 12 square root 15 plus 18 square root 10, there's no way to simplify this any further because all the square roots don't have numbers inside them with repeated prime factors. So 21 is equal to 7 times 3, 14 is equal to 7 times 2, 15 is equal to 3 times 5, and 10 is equal to 2 times 5. So none of these numbers have repeated prime factors, which means we can't simplify these square roots any further. And then all these square roots don't have any terms in common, so we also can't combine like terms. So this would be our final answer. So here's another problem type. How do we simplify something like 1 plus square root of 2 all squared? Well, you can recall from the perfect squares formula, a plus b all squared is equal to a squared plus 2ab plus b squared. So we need to apply this to our example. So the a squared in the formula of a plus b squared is just the first term squared. So this is just equal to 1 squared. And then the 2ab is basically saying it's 2 plus 2 times the first term times the second term. So the first term is 1 and the second term is the square root of 2. And then the plus b squared is just the second term, which is the square root of 2, all squared. So now all we have to do is simplify this expression further. 1 squared is just equal to 1. 2 times 1 is 2, so we write a plus 2, and the square root of 2 stays the same. So the middle term is just 2 square root of 2, and the square root of 2, all squared, is just equal to 2. So now we can combine like terms, since 1 plus 2 is equal to 3, which is the first and last terms, and then the plus 2 square root of 2 stays the same. So the final answer is just 3 plus 2 square root of 2. So here's another example. How do we simplify the square root of 2 plus the square root of 3 all squared? Since the expression is the sum of two terms in brackets all squared, we can use the perfect squares formula. So this is in the form of a plus b all squared. So the a squared in the a squared plus 2ab plus b squared term is just the first term all squared. So that's square root of 2 squared. And then the 2ab term would just be 2 times the first term, which is the square root of 2, and then times the second term, which is the square root of 3. And then plus b squared, which would be the second term all squared. So that's the square root of 3 all squared. So as always, we just need to simplify this expression now. In the first term, square root of 2 squared is equal to 2. And in the second term, 2 times the square root of 2 times the square root of 3 is equal to 2 square root of 6. And in the last term, square root of 3 squared is equal to 3. So now we can combine like terms because 2 plus 3 is just equal to 5, and the 2 square root 6 stays the same. So this expression is just equal to 5 plus 2 square root 6. So here's a slightly different example. How do we simplify 4 square root of 3 minus the square root of 5 all squared? This is in the a minus b all squared form because there's a minus sign in the middle instead of a plus sign. So we need to use the formula a minus b all squared is equal to a squared minus 2ab plus b squared. So the a squared term is just equal to the first term all squared. So that's 4 square root of 3 all squared. The minus 2ab term would be minus 2 times the first term, which is 4 square root of 3, times the second term, which is the square root of 5. And then the plus b squared term is just the second term, which is the square root of 5, all squared. So we need to write a plus square root of 5 all squared. So now we can simplify this expression, and 4 square root of 3 all squared is just equal to 16 times the square root of 3 all squared. And then minus 2 times 4 square root of 3 times square root of 5 is equal to minus 8 times the square root of 15, because 2 times 4 is equal to 8, and then the square root of 3 times the square root of 5 is equal to the square root of 15. And then square root of 5 squared is just equal to the plus 5. So now we can simplify this even further because square root of 3 all squared is just equal to 3. So this is just 16 times 3, and then minus 8 square root of 15 and plus 5, this all stays the same. And then 16 times 3 is equal to 48. And then, as always, minus 8 square root of 15 and plus 5 stays the same. So now we can combine the 48 and the plus 5. That equals 53. So this entire expression is just 53 minus 8 square root of 15. And this is our final answer.